Today we turn our attention to friction, which is probably the most important application of Newton's laws. Surfaces that are in contact usually exert forces on each other to prevent slipping or to attempt to prevent slipping. This is called friction. The actual physical origins of friction are pretty esoteric and not entirely understood even today. Your textbook offers a common but somewhat naive explanation, which we'll talk about later. And then we'll talk a little bit about what the best understanding of what the real model is, but we really don't understand it very clearly. It's actually quite hard to get friction from first principles. The effect of friction, though, is relatively straightforward, and we'll be able to handle pretty well. Cora is holding her textbook against the wall by pushing on it horizontally. So imagine here's her hand, and she's pushing it that way. Draw the free body diagram for the book. Drawing free body diagrams is mostly a checklist. We draw the weight because there is always the weight. It's the only non-contact force we're going to worry about extensively. We also know that she's pushing on the book, so we should draw that as a force from her, and we'll call F sub P for pushing. Because she's pushing on the book, the wall pushes back. Right? The book is trying to move into the wall and pushes against it. The wall pushes back. That's obviously some sort of normal force. And then finally, it isn't sliding against the wall, even though there's a force of gravity pulling down it, so there must be a force pushing upward, which is the frictional or static frictional force. So something like that. Reinhold applies a horizontal force of 35 newtons on a heavy crate, but it does not slide. What can be said about the force of static friction? And the question here is it more than 35 newtons, equal to 35 newtons, or less than 35 newtons? These are the options we're talking about. So think about it for a second. It has to be that the frictional force is exactly equal to 35 newtons. In other words, if we draw a free body diagram, we know that Reinhardt is pushing over at 35 newtons, and the frictional force is pushing back, but the acceleration is 0, so these two forces must be equal. If the frictional force were more than 35 newtons, then the block would slide in the direction of, it would have slid that way, which doesn't make any sense because it's not moving. It does not slide. The magnitude of static friction adjusts itself, increasing to prevent the object from slipping. We call such a self-adjusting force, and I'm really not kidding here, a so-called magic force. That's obviously meant in jest. We don't think there are little pixies going around doing magic on the object. A more technical term is a constraint force, a force that is as large as is needed so as to maintain some observed constraint on the system. That something happens or doesn't happen, and the force is whatever needs for that to be the case. For instance, in the last problem, the frictional force needed to be 35 newtons because we saw that the block did not slide. Right, so to make that observation true, we inferred the existence of a frictional force of 35 newtons. An important fact, though, is that a given surface will have a maximum static frictional force that it can apply. In other words, it can't always keep pushing back. Sometimes it sort of just gives up. If the required static friction is greater than that value, the object will slip, in which case static friction will no longer apply. The maximum static friction depends on the normal force between the surfaces. The harder you push two things together, the less likely they are to slip past each other. You know that if you've ever been carrying something and felt it starting to slip, you clamp down on it harder. You know that the harder you push them together, the less likely two objects are to slide, the less they can slide. Maximum static friction also depends on the materials that make up the surfaces. That also kind of makes sense. You know, it's different trying to grip something on something slick like plastic as opposed to on something, say, rough like carpet. We express that through a dimensionless number called the coefficient of static friction, written mu sub s. This is the Greek letter mu. You spell it or transliterate it as mu. It's pronounced as, you might imagine, an M following it by U, literally mu, mu. And it's written sort of like the offspring of an M and a U. It is the Greek equivalent to the letter M, but it's not an M. So learn how to write it, because it's very bad if you start writing it as M, and then you also have masses written as M, and either you get confused, or I get confused, or eventually the grader gets confused. We can then write the maximum static frictional force as the F sub S max is mu S times Fn. And you're going to want to kind of keep this in mind, commit it to memory, or at least know where to find it. The maximum static frictional force is mu S times Fn. It can be less than that if it needs to be, but it can't ever be more than that. Important to understand that mu s is not a universal constant. That is, it's not like the gravitational constant or even quasi-universal like little g being 9.8 meters per second squared everywhere on Earth. The specific value of mu sub s is determined by the microscopic details of the materials involved. It's not something you're expected to know, it's something measured and or looked up in a table. Sometimes the question might say find mu, but you're not expected to know mu. Over here your textbook has offered up a couple of different values for mu s. Rubber on concrete, which is a relatively heavy and frictional thing, is a mu of 1, whereas all the way down to ice on ice is only about 0.1. That's the general range you'll see on real-world objects, between about 0.1 and about 1, but there's no hard and fast limits on either end. Mu can be bigger than 1 with no problem, and it could be less than 0.1, although it tends not to be in human terms, in things that we tend to run into. So a couple of example problems. A box on a rough surface has a rope attached to it. The rope is pulled with tension T as shown. The coefficient of static friction is mu sub s. The box does not move. Which of these statements must be true in this situation? All right, let's pull out the important things. The box does not move. That's important. Also, we're given some things, the tension T and the coefficient mu. If the box doesn't move, though, we know that the forward force of the tension must be resisted by a backwards force of friction, and they must be the same size. So we end up with this. In other words, mu wasn't relevant here. We had other information that gave us the condition without using it. Also, be forewarned about this one, which is very tempting. This is the maximum Fs, not necessarily the Fs that we see. All right, a box weighing 100 newtons sits at rest on a level table where the coefficient of static friction between it and the table is 0.45. What is the minimum horizontal force in newtons that is needed for the box to slide? Well, if we want the minimum force for the box to slide, that's just more than the maximum force where the box doesn't slide. So if I draw a free body diagram for the box, and we know that we are applying some force to it, but we know there's a frictional force which is pushing back, and we want them to not slide, then the frictional force minus pushing force minus frictional force has to be ma, which is 0. We also, of course, have a weight and a normal force, and we see that in addition to the horizontal forces being 0, so, of course, are the vertical forces. So we can turn this into saying FF is FP, and we know that FF is mu Fn. And if we want the maximum force we can push without it sliding, which is just less than the minimum that will cause the slide, then we need the maximum value, so we can put that equal sign there. And we know here that Fn is Fg. So this becomes mu times Fg, or 0.45 times 100 newtons. 45 newtons is the most that you could apply. Anything more than that, and it would slide. Or the minimum force you could apply is anything more than 45 newtons. And so we return to Cora. Cora is holding her textbook against the wall by pushing on it horizontally. The smallest force she can apply before the book slips is 22 newtons, and the book weighs 12 newtons. What is the value of mu s? So we must have the maximum static frictional force, because if she reduces her pressure even a little, it slides, so it must be right on the edge. You might remember, or we might draw again, our free body diagram, which is the weight of the book downward, Cora pushing into the wall resisting that, and then the wall resisting the fact that it should not slide. So we end up with, if we do our little process, that's step 2 in our process. Step 3 are constitutive equations. Well, we know Fg equals mg. Don't know if that's going to be useful or not. We know that that is 12 newtons. We know that Fp was given as 22 newtons. And then we have our new equation here, which is Fs max is mu Fn. Step 4 says write the net force based on the diagram. So up here I have an Fp and an Fn, but they disagree on direction, so one of them should have a minus sign. And likewise, in the y direction, I have an Ff and an Fg, but they disagree in direction, so one should have a minus sign. Step 5 says write expressions for A, but that's easy because ax equals 0 and ay equals 0. And step 6 says write fnet equals ma in each direction. And then we get the maybe meat of it, which is step 7, which says substitute and solve. Well, step 8 says solve. So we have Fp minus Fn equals m times 0 or 0. And Ff minus Fg equals m times 0, which is 0. This tells us that Fn is Fp and Ff is Fg. And you might not have needed all 7 steps to get here, but that's where we are. You could have seen that ahead of time and simplified it. As always, the recipe here is probably overkill, but always works. Finally, we can say, well, mu s is the maximum static frictional force over the normal, which in this case is the weight over our pushing force, which is 12 newtons over 22 newtons, which turns out to be just about 0.45. And so that would be the coefficient of static friction for this situation.